again. Trying to record this stuff. Okay. Last time we okay. Let me find the spot where we were last time. I think we dealt with semantics. Yes. Just to recall this stuff, we dealt with the semantics of predicate logic, and in contrast to the semantics of propositional logic, where you just to give meaning to a formula have to say what the propositions, whether they are true or false. In predicate logic, we've seen that this is a bit more complicated. We need a model that tells us through all the predicates with what subsets it starts with a domain of individuals about which we are reasoning. Then we introduce predicates that can be either still propositions, so they are global facts, or they can be unary predicates, which mean they actually stand for a property of such individuals, and they semantically are represented by subsets of the domain. Binary predicates, which correspond to binary relations over your domain, or in other words, sets of pairs, etc. And the third component is to assign meaning to the constants in your vocabulary, and the constants simply stand for individuals from your domain. So that is what a model is, and we discussed this in some detail, giving some examples of abstract predicates interpreted over particular domains. Okay, and then it turns out that this terminology of model is just lifted from propositional logic to predicate logic, and we can reuse and immediately reuse many of the concepts, such as satisfiability being the existence of a model, or logical equivalence being two formulas that have exactly the same set of models. And this doesn't change from one logic to another. Once we've established what a model is, you can just apply these terms all over again. So, validity then is, I think we stopped about here, but maybe you can confirm or deny this. Did I actually come back to the notion of validity?
I don't think so.
No, but there's no great surprise here. I mean, validity already meant a formula in propositional logic is valid if and only if all possible models are indeed models, right? If the entire domain of possible models indeed satisfy this formula. And the same holds for predicate logic. So a valid formula in predicate logic is one for which all models satisfy that formula. And you may think of fairly obvious properties, such as the fact that whether you quantify over one formula and then another, the order of exists some x such that there exists some y such that a formula of 5 of x and y holds is equivalent to there exists a y such that exists an x such that the same formula holds. In other words, the order in which you quantify over variables is not important for the meaning of the formula, and so saying that these two are equivalent therefore gives you a valid formula in itself. Which, by the way, it is not necessarily true if the quantifiers are different. So this is valid because I'm using the same quantification twice. I could also write the formula saying that for all x exists y such that phi xy is equivalent to exists y such that for all x phi xy, but this is not a valid formula. So what does it mean that it is not a valid formula?
There exists interpretations that do not satisfy this formula.
Yes, there exists at least one interpretation for which this formula is not satisfied. Can you think of such an interpretation for which this formula is not satisfied?
Yeah, I think so. It's a little bit convoluted.
So we are looking for an interpretation in which one of these operands of the equivalence is true, and the other equivalence, the other operand is false.
So take the domain to be.
Yeah. Okay.
No, yeah, I just want to make a wild guess, but I think that the right hand side said there is also a y which doesn't hold for, or there's a situation where all x doesn't hold for a y because it's only for some y, and that's not what the other side says.
So, for example, take the domain to be all negative and positive integers.
Yes.
And then say that the predicate says that the sum equals 0.
Mm-hmm.
So then you say that every x, for every x there exists in a y such that you can, when you sum them, they make 0.
Yes.
But conversely, it's not true.
Yes. So in that domain, where the domain consists of all integers, positive and negative, the formula expresses that the sum of two integers equals 0. In that interpretation, this subformula would hold because it is the case that for all numbers there is an inverse, together with which it sums up to 0. Whereas this operand would be false. It is not the case that there exists a number such that for all other numbers the sum is 0. Yeah, so we have an interpretation for which this subformula evaluates to true, and this subformula evaluates to false, and therefore the equivalence itself evaluates to false. Okay. This all to illustrate the notion of validity, and I want to stress that that notion in itself really hasn't changed from propositional logic. It's just the interpretation, the nature of the interpretations that has changed, and all the other terminology just continues being usable. If you would want to show the validity of such a formula, then you would have to reason about all possible interpretations. That seems a bit difficult, but let me give one example to give you a flavor of how that would work. So without the help of any additional machinery like tableaus or proof systems, let's think about showing how to show that this last formula is valid. And the formula says that for all x, phi x or psi x implies that for all x, phi x, or there exists an x such as psi x. And if you think about this, left-hand operand says that for all x, either one property holds or another property holds. So for all numbers, either they are even or they are odd would be an example of that. And the formula as a whole says that implies that either for all x, the first of these holds, so either all numbers are even, or there exists an odd number. Okay, I hope you agree that this sounds very reasonable, but let's think about how to show this to be valid. Well, to show it to be valid, you can start by looking at the operator of implication, and you can realize that if the first operand of implication is false, then we're done immediately. Because that's how implication works. If the first operand is false, then the implication holds. So that case is immediately covered. So we actually only have to look at the case where the first operand is true. So let's assume that we are in a model where the first operand is true. That means that the first operand evaluates to true under your valuation function. Okay, now we have to think back what that meant. What does this valuation do for the case of universal quantification? Anyone? What does the valuation, how does it compute the value of a universally quantified formula? Remember that this sigma here is an assignment which assigns to all the variables in your formula an element of your domain. So we have an assignment sigma, which assigns to all the variables in phi and in psi some value from your domain. But here we're quantifying over x. And the idea of this quantification is that the value of this x and the value of that x are not fixed by this sigma. Instead, the idea is that whatever value we pick for that x, phi x and psi x both have to be evaluated true. So we want to evaluate the inner formula without the quantifier, but we want to evaluate it not necessarily using the assignment sigma that we start with. Instead, we want to pick an arbitrary value for the variable x, modify the assignment such that the modified assignment assigns that arbitrary value to x, and then the inner formula has to evaluate to true. Okay, that's written out like this. In order for this universally quantified formula to evaluate to true, what has to be the case is that whatever value we pick to assign to x, either phi x has to evaluate to true for that modified substitution, or psi x has to evaluate to true for that modified substitution.